So we talked about the Marshall mix design a little bit last session, and we started talking about the SuperPave mix design, and we covered the basics, and we will now talk about the components of the SuperPave mix design process. The first components, are probably one of the major components of the SuperPave or any hot mix asphalt mix design, is first of all the aggregates, right? So we're going to talk about aggregates, and there are specific size definitions for aggregates in the SuperPave mix design or mix design terminology. So we're going to talk about that. The aggregate size definition, aggregate size definition for SuperPave purposes. And we have two somehow similar to the general terminology that we use usually for aggregates in the past, but this time a little bit different. So we have nominal maximum, maximum aggregate size, which is one size larger than the first sieve that retains more than 10%. So the definition is one size larger than the first sieve, to retain more than 10%. So you do the sieve analysis and you know the percent retained on each sieve. And the first sieve that you have more than 10% retained, the sieve on top of that one will be the nominal maximum aggregate size. And then we have another definition, which is just maximum aggregate size. So that was the nominal maximum aggregate size, and then we have a maximum aggregate size, which is one size larger than the previous one, or so one size larger than nominal maximum aggregate size. Okay, so maximum aggregate size is one size larger than nominal maximum aggregate size. Right? And again, we're going to have an example and show you exactly what these mean. Okay, now there is a certain specification or certain requirements for aggregate gradation for SuperPave purposes that I'm going to show you now. So let's say this is your aggregate gradation curve. The y-axis is, again, this is our gradation curve, so y-axis is percent passing. And if you remember, we had in one of the examples, we had the sieve analysis or aggregate gradation. For the regular sieve analysis, when you want to plot the curve, the x-axis is on a log scale, or you're basically showing the aggregate size on a log scale, or it's a semi-log graph. But for SuperPave purposes, the x-axis is basically you raise the aggregate size to the power of 0.45 instead of using the log scale. So the definition of the x-axis is sieve analysis, not sieve analysis, sorry, sieve size or grain size in millimeter raised to the power of 0.45 power. And when you do that, you should be able to receive or to get a straight line like this. And there are some control points on this line. So if I select this one, let's say this is 0.075. That's sieve number 200. Then we have 0.3, right? So we have 0.3. Then we have 2.36. We have 4.75. We have 9.5, 12.5, and 19. So that's our typical sieve size numbers. And then there are these control points that you need to be within. So there are 2 control points for sieve number 200. There are 2 other control points for sieve size 2.36. These 2. There's one for 9.5. It's up here. And there are actually 2 up there, 2 more up here, and there's 1 over here. Right? So you call these control points. And then there's also a restricted limit or restricted line or restricted zone here. So this is restricted zone. And then from the previous definition, let's say this, as an example, this can be the nominal maximum aggregate size. And then we said that one sieve larger than that should be just maximum size, maximum aggregate size, right? So how do we use this graph? Let's say you have your gradation curve in the x-axis to raised to the power of 0.45, and your gradation curve might look like something like this, right? This is a perfect example that is acceptable. However, if your gradation looks like this is not acceptable, because over here you're not within the range, over here you're in the restricted zone, here you're outside of the range, here you're outside of the range, and so forth and so good, right? So these are the things that we need to consider for the aggregate considerations. So not acceptable, and the other one is acceptable. Right? So that's how we check for our aggregate size distribution. And there are some specific sieves in the SuperPave designation or SuperPave specifications. So you call those SuperPave mix size designations. So if I'm going to show these in a table, it'll look like something like this. So SuperPave, SuperPave mix size designations. So for example, if your SuperPave designation, so SuperPave designation, if the SuperPave designation is 37.5 millimeter, then the nominal maximum aggregate size, NMAS, so we can probably define these up here. This is NMAS, nominal maximum aggregate size. This is MAS, maximum aggregate size, right? So the nominal maximum aggregate size for this one will be 37.5 millimeter, and then the maximum size, maximum aggregate size, these are in millimeters, will be one size above that, which is 50. And then we have 25 over here. So of course, this is 25, and one size above is 37.5. Then we have 19. One size above is 25. We have 12.5, 5 and 19, and then we have 9.5. And there are some considerations for aggregate gradation. So aggregate gradation considerations, aggregate gradation considerations, which are the following ones. So the maximum, the first one is that the maximum size, the maximum aggregate size should be less than 1/2 of the AC lift thickness. And AC is asphalt concrete, right? Of course, AC is asphalt concrete. And then the applications or the implications of larger maximum size are that it increases the strength. So increases strength. It also improves the skid resistance. So improves skid resistance. It increases volume and surface area of aggregate. So increases volume and surface area. It also improves the rutting resistance or permanent deformation, so improves. Oops, sorry. So improves rutting resistance. And it also increases the chance of segregation. So increases problem with segregation. And on the other hand, if you're using a smaller aggregate size, you will have less problem with segregation, so reduces segregation. It also reduces the road noise. If you paid attention, then while you're driving on a coarser aggregate asphalt surface, you will hear more noise compared to a more finer aggregate that asphalt layer is built of. So it reduces noise, reduces road noise, and it also decreases tire wear. So decreases tire wear. Right? So those are the considerations for the larger or lower or smaller aggregate size. And then there are a number of other considerations for the number of crushed aggregates in gravel, or number of crushed faces or crushed fragments in gravels. So that's called percent crushed fragments. In gravels. And the considerations are, if you are using quarry, the materials from a quarry, so quarry materials has to be 100% crushed. And the minimum value depends on what traffic level you're designing for and what layer or what lift you're designing for. So the minimum values. So minimum values depends on design traffic level. And also the lift of layer, right? And that percentage is defined as percent of mass of aggregates with one or more fractured faces or crushed faces. If your aggregates have one or more crushed or fractured faces, then you will consider that the mass of those percentage of aggregates into percent crushed face in the aggregates. And the reason you don't want to have round aggregates in your asphalt pavement is so rounded aggregates in asphalt is because if you have a layer of round aggregates all around, right? The problem with that is that when you have the traffic load, there's going to be, since there's no friction between the crushed faces, once you have the traffic load, the tire load, there's going to be a shear plane. And aggregates are going to slide on top of each other. Then you have rounded aggregates. So we don't want to see that. And then there's a minimum or a specification for coarse aggregate angularity criteria that I'm going to post the paste table up here and post it on Canvas. So coarse aggregate angularity criteria, coarse aggregate I'm going to insert the table based on traffic level in terms of millions of easels and depth from the surface. You should be able to see, of course, for higher levels of traffic here, you will need 100% crushed faces or angularity in your aggregates. Okay, so that's pretty much all we need to know about the aggregate in the SuperPave mix design, and then we need to move on to the asphalt cement or asphalt binder. So as a brief background, there is a difference between asphalt and tar. So asphalt is soluble in petroleum products, so soluble in petroleum It's also generally a byproduct of petroleum distillation process. So byproduct of petroleum distillation process. And in some cases, it can be naturally occurring. So you can have natural asphalt. So it can be naturally occurring. And then on the other side, we have tar, which is resistant to petroleum products. So resistant to petroleum products. It's also generally a byproduct of coke or from coal mining process. So generally byproduct of and so that's it. So for making the hot mix asphalt, we definitely using asphalt. And as we mentioned before, the traditional method for categorizing or classifying different types of asphalt was only based on penetration, that you basically drop a needle into the asphalt sample and you measure the penetration after 5 seconds. So the traditional classification system was based on penetration testing. That you have your asphalt sample. This is the asphalt sample. And then you just drop a sewing needle. This is a 100-gram needle. You drop it and then you measure the amount it penetrates after 5 seconds. So again, the same container. You have your asphalt sample here. And then your needle is already dropped here. So this is the amount it penetrates. You measure the penetration in 0.1 millimeter and you measure it after 5 seconds. So after 5 seconds. And based on that, we used to have 5 grades based on range of penetration of the asphalt samples, so 5 grades. And we used to classify the asphalts based on these. For example, we would say you need a 40-50 asphalt or a 60-70 asphalt layer for this project, asphalt binder for this project. So 40-50, 60-70, 85-100. 120, 150, and then 200, 300. And of course, the higher the penetration, it shows that the softer the asphalt binder was, and for colder regions, we would use a higher penetration rate, and in hotter areas, you would use a stiffer binder, right? The other test that was used to classify the asphalt binder was the ductility test, that you had basically a mold with asphalt samples here and here, and it's basically a small asphalt sample that you pull from both sides, and you measure how much ductility in a centimeter scale you have for your asphalt sample, right? And then there were two other criteria as flashpoint, the temperature that the asphalt starts to ignite. So flashpoint of the asphalt, and also the solubility if in percentage. This is in usually degrees Celsius or degrees Fahrenheit. And ductility is in centimeters. And then there was, at some point, there was a grading system based on viscosity of the asphalt binder. And at different temperatures, you have different viscosity. Of course, at higher temperature, you have lower viscosity, and vice versa. And there were two types of viscosity tubes. So viscosity grading, viscosity grading by measuring the viscosity tubes. And that's pretty much all we had for the traditional or conventional mixing or classification of the asphalt binders. And then with the introduction of the SuperPave system mix design process, they've also reviewed the binder classification very thoroughly, and then they came up with the PG specification system. So PG specification system or just PG specifications, and that we mentioned that the PG is basically performance grading, performance grade of the asphalt binder. And there were some benefits, or there were some fundamentally or fundamental properties considered in this new specification or classification system. So the advantages is that it is considering the fundamental properties related to pavement performance, related to pavement performance. It also considers the environmental factors. It also includes and considers the in-service and construction temperatures, basically one of the main classification criteria, in-service and construction temperature. And also short and long-term aging. So the aging of the asphalt or oxidation of the asphalt was not considered in the previous classification system, but in the PG specifications, we have both short-term and long-term aging. So long-term aging. Okay, so if we want to show an example of the PG grading system, this is how we would show a PG asphalt. PG so PG, oops. As an example, we have PG 64 negative 22. Again, we mentioned this last session, but pay attention to this one, that how you read or how you spell the PG grades. It's not PG 64-22. It's basically PG 64 negative 22. And of course, the PG represents the performance grade, right? So performance grade. The first number is the average 7-day maximum temperature of the asphalt. So 7-day maximum pavement temperature. And the second number is the minimum pavement temperature. That's why we read it as 64 negative 22. And pavement temperatures are calculated using a software, SuperPave software, that is available online. The high temperature is measured at 20 millimeters below the surface. So measured at 22 millimeter below the surface. And then the low temperature is actually measured at the surface. So measured at the surface. And the pavement temperature generally, so pavement temperature is a function of ambient temperature or air temperature, right? As well as the depth, at what depth we are measuring the temperature, and also at what geographical location. So the latitude or geographical location. And again, these are calculated by software. We have different regions, climate regions in the US, and by entering your location, your GPS location that you want to design the pavement for, you should be able to calculate the maximum and minimum pavement temperature from the software. And then there are specific tests that are that was designed specifically for the SuperPave that I'm going to list here. We don't go into the details of these tests, but we need to know what each test is measuring and how we use the information from each test in our classification system and in the PGS specification table. The first one is called the concentric cylinder rheometer. So concentric cylinder rheometer. The next one is the DSR test, so dynamic shear rheometer, or DSR. As we mentioned, we are considering both short-term and long-term aging of asphalt. For the short-term aging, so short-term aging, we are using an equipment that's called rolling thin film oven. So rolling thin film oven, or we call it RTFO. And basically what it does, it simulates the aging process during the construction and mixing at high temperature. So simulates, that's why we call it short-term aging. Simulates aging from hot mixing and construction. That's the short-term aging. And if you want to consider the long-term aging over the life of the pavement, for long-term aging, you would use a pressure aging vessel. So pressure aging vessel, or PAV. This is basically simulates the aging over the 7 to 10 years. It simulates in under high pressure. So simulates aging for 7 to 10 years. And the process is that we take a 20 gram, I'm sorry, a 50 gram sample. So 50 gram sample is aged under pressure for 20 hours. And the pressure, under the pressure of about 2000 kilopascal, which is around 300 psi. And we do this at different temperatures. So at 90 degrees, 100 degrees, and 110 degrees. These are all degrees Celsius. The next test that we use to classify the binders in the PG system is called bending beam rheometer. So bending beam rheometer. That's actually a thin beam of the binder sample under pressure, under a load applied at the center of the beam, and we measure the bending of the beam using the equipment. The next test is the direct tension test. So direct tension test. That you basically have a sample and you apply tension to the sample and you see how much tension it takes to break the sample into two parts. That's by applying direct tension to the sample, right? Now, if you want to summarize all of these together on a timeline, if you start with the construction level, so at the construction level, we do the RV test. And this is the timeline or life of pavement. And then under service, when we start to see the rutting or permanent deformation, we use the DSR test to estimate or to predict the rutting or cracking, when the rutting or cracking happens. So DSR is actually coming between these two, for both of these. So DSR and just the type of sample that you're using is going to be different for these two. And then for low temperature cracking, so low temperature cracking, we would use a direct tension test or DTT, or bending beam rheometer or BVR test, right? And so we call this DTT and then BVR. Okay, so going back to the timeline, starting from the construction until about these areas or these times, you have pretty much no aging, right? And then after that, you simulate the aging from this stage until somehow the end by using the RTFO, the rolling thin film oven, for the short-term aging, right? So for short-term aging, and then for longer periods like these ones, you use the PAV or pressure aging vessel for simulating the long-term aging.